Hello, welcome back. This is Ms. McClellan here to go over IM2 5.2.1 with you. All right, our learning goals are as follows. Number one, by the end of this lesson, you should be able to, I'm going to write this in first person, I will be able to, one, solve quadratic equations in perfect square form and express their solutions in both exact and approximate forms. Number two, you should be able to determine the number of real solutions to quadratic equations written in perfect square form. So I'll start with 5-59. Solve the following equations. This is a bit of a review. In order to solve these equations, we need to get all of my terms on the same side of the equation. So here I'm going to add 16 to both sides. That's x squared plus 8x plus 16 equals 0. And then I'll factor and solve for x. All right, I know I need to multiply to 16 and add to 8. 4 times 4 will do that. This becomes x plus 4 squared equals 0. Notice I skipped the box. You can actually do that when the coefficient of x squared is 1. Here, I'm not going to skip the box because the coefficient of x squared is 4, which means I won't be able to take my answers directly from the sides of the diamond problem. Okay, so we've got 4x squared. I need the box. I know I need to multiply to 100 x squared because the diagonals have to multiply to the same thing. And I know I need to add to negative 20x because when I add these two boxes together, I have to get negative 20x. Okay, that's going to be negative 10x and negative 10x. Okay, on the outside, this is 2x times negative 5, and same up here and down there. So this becomes 2x minus 5 squared equals 0. It's squared because it's the same thing being multiplied by itself. All right, I'm going to subtract 12x from both sides on this one. This becomes 4x squared minus 12x plus 9. Again, I'm going to need that whole box. This is 4x squared, 9. 9 times 4 is 36. I need to multiply to 36 and add to negative 12x. Well, negative 6 will do that. Negative 6 times negative 6. And then I'm going to have 2x times negative 3. So this becomes 2x minus 3 squared equals 0. I'm not done because I was asked to solve. So I'm going to solve each of these. Zero product property tells me that I can just set what's inside these parentheses to 0x. And that's because I'm equaling to 0. X plus 4 equals 0 tells me that x is negative 4. I only have one solution because even if I wrote this out the long way, they would both get me the same thing. This has only one solution. You get it from doing 2x minus 5 equals 0, add 5 to both sides. 2x equals 5, divide both sides by 2. X is 5 divided by 2. Here again, I have 2x minus 3 equals 0, add 3 to both sides. I get 2x equals 3, divide both sides by 2, and I get x is 3 halves. Okay, next problem. 5-60. In problem 5-59, did you notice anything special about the forms of the quadratic equations you wrote? Did you use the zero product property to solve your equations, or were you able to solve them in a different way? Without rewriting, determine the values of x that make each of the equations true. All right, so what they're talking about here when they say, were you able to solve it a different way? Some of you may have noticed that I could have taken the square root of both sides for each of these equations. And that's what I'm going to do down here. I have x minus 1 squared equals 4. I'm going to take the square root of both sides, and that gets me x minus 1, this cancels, equals the square root of 4. Now be careful. There's actually two ways that this could happen. This could be -2 or +2. Reason being, because -2 squared is 4 and +2 squared is 4. And either of those situations would be solvable for x. So this becomes two different equations. X minus 1 equals 2, or x minus 1 equals -2. Oops, need more space. Add 1 to both sides for each version. And we get x is either 3 or -1. Two solutions. Okay, this one. I have x minus 1 squared equals 0. I take the square root of both sides. I get x minus 1 equals, and it would be plus or minus 0, but that doesn't make sense to say plus or minus 0 because 0 is non-negative always. So I'm just going to write x minus 1 equals 0. Therefore, x has to be +1. Again, here I have x minus 1 squared equals -4. I take a square root of both sides. And if you throw this in your calculator, if you throw the square root of -4 in your calculator, you get an error message. And that's because in the real number system, that's all numbers from -infinity to infinity. -4, the square root of -4 is not a member of that number system. We would say no real solutions since the square root of -4 is not real. There are no two real numbers that I can say multiply to equal -4 if I'm multiplying them by themselves. Coming up in section 5.2.6, which we're going to do out of order because I want this to happen a little bit sooner, we'll see that this does have solutions. They just don't show up on our graph. And that's because our graph is two-dimensional, and these solutions would pop out. It has to do with electricity. It's kind of amazing. Anyway, let's do 5.5-61. The quadratic equation x minus 3 squared equals 12 is written in perfect square form. It's called that because the expression x minus 3 squared forms a square when built with algebra tiles. Solve x minus 3 squared equals 12. We'll write our answer in exact form or radical form. Okay. So I'm going to take x minus 3 equals 12, and I'm going to take the square root of both sides. X minus 3 squared, rather. And that gets me x minus 3 equals plus or minus the square root of 12. Now, you could simplify that to make it say 2 root 3 if you want. But what I'm really looking at is the fact that if I put the square root of 12 in my calculator, and I'll do it right now. So square root of 12, I get this number. And this is a number with a decimal that will never end. That's not exact. They rounded to the decimal place. 1, 2, 3, 4, 5, 6, 7, 8, 9. My calculator rounded to the 9th decimal place, and I don't want any rounding at all. So when I actually am going to write, after I split this up into two equations, x minus 3 equals positive root 12, and x minus 3 equals negative root 12, I'm going to leave the radical, the square root symbol in my answer. X is going to be equal to, if I add 3 to both sides, to cancel on the left, 3 plus root 12 and 3 minus root 12. And those are my two answers. Just want to make it more obvious. There's a minus sign right here. Okay. How many solutions are there? Well, there are 2. They asked that question because they want to make sure that you do the positive and negative square root. The solutions from part A are called irrational. That is, they have decimals that would never repeat or end. We're going to write the answer now in approximate decimal form. Here we go. I will round to the nearest 100. So this becomes, getting our calculator back, 3 plus 3.46 or 3 minus 3.46 with a final answer of x equals 6.46 or negative 0.46. This is approximate decimal form. I use the decimal version of my answer. These are pretty much the same, except this is more exact. And I rounded it to my 100th digit. Approximate form is not always to the 100th digit, but sometimes it is. And in this case, that's the one. Next page. Okay, the number of solutions. The equation in problem 561 had 2 solutions. But in problem 560, you saw that a quadratic equation might have 1 solution or no solution at all. Remind you, here's a situation where there were no solution. Yikes. All right. How can you determine the number of solutions to a quadratic equation? We're going to solve these and then look for a pattern. The pattern we're looking for should answer the question, how can we determine the number of solutions to a quadratic equation? All right, first one. Woof. Take the square root of both sides. That gives me 2x minus 3 equals plus or minus 7, because the square root of 49 is 7. This becomes 2 equations. 2x minus 3 equals positive 7, and 2x minus 3 equals negative 7. I add 3 to both sides. I get 2x equals 5. So x is 5 over 2. Here I add 3 to both sides. I get 2x equals negative 4. So x could also be, if I divide both sides by 2, negative 2. Box it. Next problem. I take the square root of both sides. I get 7x minus 5 equals plus or minus the square root of negative 2. Ooh, this is impossible. Well, it's not impossible, but we're not doing it at this level. No real solutions to square roots of negative numbers. Okay, next, square root of both sides. I get x plus 4 equals plus or minus the square root of 20. All right. Ugh, I have to do this in both exact and approximate form. I follow the rules. Okay, this becomes two equations. X plus 4 equals root 20, or x plus 4 equals negative root 20, which becomes x equals, I subtract 4 from both sides, negative 4 plus root 20, or negative 4 minus root 20. That's exact. Let's do approximate. Okay, negative 4 plus the square root of 20 equals 0.472. And let's do, when I'm subtracting the square root of 20, negative 4 minus the square root of 20, or negative 8.472. That's approximate. Okay, next problem. I take the square root of both sides. I have 5x minus 10 equals plus or minus the square root of 0, which is just 0. So I have just one equation to solve. 5x minus 10 equals 0. Add 10 to both sides. 5x equals 10. Divide both sides by 5 to find that x equals 2. Okay, next problem. Take the square root of both sides. I have x plus 2 equals plus or minus the square root of negative 10. Auga, no. This has no real solutions to square roots of negative numbers, period. Okay, next problem. This one's more interesting. X plus 11 squared plus 5 equals 5. You might go ahead and try to take a square root right away, but you can't. If I were to take the square root of this whole side, I would be trying to combine things that are not combinable. I need to subtract 5 from both sides first. This is x plus 11 squared equals 0. Now I take the square root. I get x plus 11 equals plus or minus the square root of 0, but that's just 0. So x plus 11 equals 0, and x, it must be just negative 11. Now they want me to use the patterns that I noticed. But wait, when were we going to talk about what those patterns are? What patterns do we notice? Okay. I notice personally that square roots of negative have no solutions. Square roots of 0 have one solution. And square roots of numbers have two solutions. Okay. Here, we're not even asked to solve the problems. We're just asked to decide how many solutions it will have. Well, before I can begin, just like what I had to do in part F up here, I must subtract 6 from both sides. And I have 5x minus 2 squared equals negative 6. And this is going to be no real solutions. Because if I were to take the square root of both sides, I would be taking the square root of a negative number. Next. Okay, I'll take this one. We'll have one solution. Because if I take the square root of 0, I end up with just one equation to solve, because the square root of 0 is non-negative. So that doesn't end up creating two different possibilities. This one, if I take the square root of 11, I will have two solutions, because the square root of 11 is plus or minus the square root of a number, which is positive, and the plus or minus will make me split off into two possible equations. Next problem. 5-64. What can the solutions to a quadratic equation tell us about the graph of the related quadratic function? Graph the functions below on our graphing calculator and sketch the graph of each function. All right, here we go. If you're at home, you might be using Desmos. That will work as well. Here, I have 5x. Watch me learn how to find x on this calculator. I haven't done this in years. 5x minus 2 squared plus 6. Now I press graph. Zoom. Maybe I zoom in. Window. Let's make this go from -5 to 5 and start at -2 and go up to 10. Maybe that's going to be better. Well, it's a little better. In any case, boom. I noticed that there are no x-intercepts. And if I were to plug in 0 for y here, I would have 0 equals 5x minus 2 squared plus 6. I would subtract 6 from both sides. -6 equals 5x minus 2 squared. That would be no solutions. No real solutions. So if the equation has no solutions, there are no x-intercepts. Let's look at the next one. Y equals, this one says 4x. Oh, I need parentheses. 4x. Nope. Still getting it wrong. Okay, careful. 4 plus 2x. Quantity squared. Graph. Beautiful. Oh, look, and it only has one solution. So 1 x-intercept. And that makes sense because if I were to plug in 0 for y in order to find my x-intercepts, I would be taking the square root of 0, which would only produce one possible solution. So one solution, 1 x-intercept. All right, let's see again. Now this one. Y equals 7 plus 2x squared minus 11. Oh, looks like I need to zoom. No. -10 to 10. Let's have this go down further. -10. Graph. Let's see if that's better. Ooh, good enough. There are 2 x-intercepts. Let's see. If I put in 0 for y, I would have 0 equals 7 plus 2x squared minus 11. I add 11 to both sides. Then I have 11 equals 7 plus 2x squared. And if I were to take the square root of both sides here, I would have plus or minus the square root of 11, which would end up giving me 2 solutions. 2 solutions, 2 x-intercepts. Isn't that interesting? Ooh, I forgot to draw the graph. Both of these. I'll do it right now. Okay, here's this graph. And this graph, I don't remember. I better redo it. It was 4 plus 2x squared. Graph. It's like this. Do-do-do, do-do-do-do. Just barely touched the x-axis. Okay. Moving right along, we're almost done. Last page. So this is a summary of the lesson. Notice this equation, x minus 3 squared equals 12, is written in perfect square form. And we say that because its length equals its width. So for example, a 5 by 5 square would be a square because it's 5 by 5, whereas a rectangle, something which is 5 by 6, would not be called perfect square. This is a perfect square because on either side of this equation, of this area model, we have x minus 3. The length is the same as the width. All right, 3 cases, solving equations in perfect square form. So, first case is when your perfect square is equal to 0. Next case is when it's equal to 2. And last case is when it's equal to a positive number. And last case is when it's equal to a negative number. So, when it equals 0, I take the square root of both sides, and I have here x minus 3 equals plus or minus the square root of 0, but that's just 0. So I end up with x minus 3 equals 0. I add 3 to both sides, and I have x equals 3, one solution. One solution when the quantity which is squared equals 0. All right, now I'm being equal to a number, a positive number. So I take the square root of both sides, and I have x minus 3 equals plus or minus the square root of 2. And this breaks into 2 equations. X minus 3 equals positive root 2, and x minus 3 equals negative root 2. The exact solutions become x equals 3 plus root 2 and x equals 3 minus root 2. The approximate solutions. Well, let's check. 3 plus the square root of 2 equals 4.41. 3 minus the square root of 2 equals 1.59, about. Okay, last version. I take the square root of both sides. I have x minus 3 equals plus or minus the square root of negative 2, but this has no real solutions. Please notice that I always say real. Soon we're going to learn that there are solutions. They're just not part of the real number system. Real doesn't mean real as in tangible. It means real as in something that could fall on our number line. So when you're taking the square root of negative numbers, there are no real solutions. Period. All right. Exact versus approximate solutions. In the middle equation above, the answers are x is 3 plus root 2 and 3 minus root 2. We often say this as 3 plus or minus root 2, and we call this exact because we are not rounding. All information is here. You lose information when you round, although you gain some bit of clarity because we know where 4.41 belongs in our number line, and we might not know where 3 plus root 2 belongs. Rounding creates an approximate solution because we round. Last little piece, and then we're going to say goodbye. Graphs of solutions and connections to x-intercepts. This graph has one solution. The equation has one solution. This is a little typo right here. This graph has two solutions. The equation has two solutions. This graph has no x-intercepts, and the equation has no real solutions. That's everything for today, everybody. Next class, we'll learn how to write things into perfect square form. Thanks so much for your time, and I hope you have a nice time. A nice day. Bye.